Hello, this is Team 3. This week, we will talk about the construction process of how the building was built from the bottom of the building to the highest part of the building. Construction of a building begins with the foundation. What are some important considerations before constructing the foundation? St. Mary's building is soft ground made up of acidic soil and wet soil with rivers around it. Therefore, we have to pay attention to differential sediment that can occur on soft ground. Therefore, the St. Mary's building requires a lot of files in a large size. The specification of the file is 27 meters high and 750 mm in diameter. The total number of files is 333. The files use the cast-in piles method. Through the construction of the files, constructors began laying the foundation for the St. Mary's building. The constructor installed the file on the land. After that, the file caps and files were connected so that the load of the building could be effectively distributed. First, dig out the soil of the site and support it with a mud barrier wall and a brace to prevent it from collapsing due to earth pressure. Then, put the file around the edge and center. Rebar is placed on the embedded files and concrete is placed on them in a short period of time. When the foundation is completed, the body of the St. Mary's building will be built. Gravity load, wind load, and seismic load are important considerations for skyscrapers. The main structures of the St. Mary's building consist of a core and diagrid, which has many advantages in load distribution, which is an important consideration. St. Mary's building is a skyscraper which can have relatively lower stiffness as its height increases compared to lower-rise buildings. This can cause P-delta effect, which can have a devastating effect on the structural stability of the building. To avoid such problems, the role of the core becomes important. The core mainly manages vertical loads such as gravitational loads and seismic loads, and the construction of the core part is prioritized during the construction of the building. In order to increase the robustness of the core, it was designed by dividing it into an inner core and an outer core. In addition, the inner space was left empty to accommodate facilities such as stairs and elevators. The inner core is composed of A-shaped steel connected to the column base of the foundation and acts as a pillar. Anchor bolts installed in the fixed landfill method in the foundation concrete are fixed with mortar, and after lifting the base plate, position the A-shaped steel used for the inner column and fasten the bolts to complete the core column. The A-shaped steel column made in this way enables effective transmission of the moment due to shear as well as the axial force generated by the load to the foundation. The outer core is likewise erected and a radial beam is installed between the inner core and the outer core to enhance the integrity of the core and increase the overall rigidity. This structure is constructed up to 6 floors. With the core going up, the outer tasks are also worked at the same time. A factory-prepared diagrid frame is set up. St. Mary's diagrid serves to effectively distribute its own weight, seismic load, and wind load. This is one of the most important parts from a structural point of view. This was directly connected to the main part of the building site so that the load could be distributed to the ground. Diagrid construction is largely composed of nodes and diagonal members. The A-frame of one node and two diagonal members is one unit that constitutes the diagrid structure. In addition, the building's A-frame consists of two-story triangular module. When a load is applied to the unit, the load can be effectively distributed from the node to the diagonal member. Therefore, the node part of frame A is one of the structurally important parts. Nodes are connected to other nodes through a ring beam and are connected to the core through a radial beam. Through this connection, the load can be effectively dispersed to the core by descending along the diagonal member of the diagrid. This A-frame could be stably constructed through a connection with the core using a beam. The connection process has three main procedures. First, A-frame is vertically erected. Then it is connected to the core through a radial beam, and nodes are connected using a ring beam. Therefore, by repeating this process, frame A has continuously coupled to form a steel structure that moves integrally. In the structural design of the St. Mary's building, the node part plays an important role of the overall load distribution, especially the angle of the node in the A-frame, the shape and size of the diagonal member. The higher the building, the more affected by wind loads, so the area of the upper floors was gradually reduced to control the wind flow and maintain structural rigidity. As a result, a node angle of 60 degrees was adopted on some floors and 77 degrees on others to achieve optimal load distribution, considering the area and height of each floor. 18 of these nodes were placed across each of the two layers and a total of 360 nodes were used. In addition, the stability of the structure was increased by using hollow section structure diagonal members with excellent rigidity efficiency, and the size of the upper and lower layers were set differently, enabling more efficient and accurate load distribution. Diagrids, which play an important role in structures, are more sensitive to construction errors. What kind of efforts have been made to reduce construction errors? First of all, in order to reduce the error in the fastening of the node and the diagonal member, the factory accurately processed the junction of the node and the diagonal member through the CNC milling method and the slot hole method. After placing the factory-made diagrid at the correct location of the members to maintain the adhesion and spacing of the node and the diagonal member at the site, the construction error could be reduced through contemporary tightening. After the overall connection between the diagrid and the core, the slab construction is carried out. This process is constructed using deck plates, stud bolts, wire mesh, and concrete. First, connect the deck plate to the radial A-shaped steel beam. Weld the stud bolts, lay the wire mesh, and finally pour the concrete. At this time, the stud bolt guarantees the integral behavior of the concrete. The concrete used for pouring was also unique. Litex lightweight concrete was used to reduce its own weight, making it possible to reduce the weight of the structure by about 23%. The weight of the slabs reduced in this way could reduce the load on the structural member. And it has become possible to allow the same amount of sagging with a thinner slab thickness than a slab using ordinary concrete. And St. Mary's has a characteristic internal structure that has void space on each floor and rotates by 5 degrees as it goes up one by one. This is for lighting efficiency and natural indoor air circulation, which helps save energy. We are going to talk about how the curtain wall of the building was constructed. The exterior of the building, which has a round shape, is designed with oblique steel beams and 5,500 double glasses in the form of diamonds. The spiral striped diamond pattern on the exterior further emphasizes the building's natural lighting and ventilation functions. Due to the natural London's weather, which has many cloudy and rainy days, the curtain walls of buildings had to take full advantage of the lighting effect. Therefore, by controlling the indoor temperature through solar measurement through the curtain walls, it resulted in energy savings of about 40%. The curtain wall of the building used the univall system. The exterior of the building is covered with a diamond-shaped facade. On the horizontal beams located in layers, brackets for substructure members of curtain wall finishes were planned. Each facade was pre-made in a factory and shipped to the construction site. Then, in the field, constructors connected the facades to the bracket part installed on the diagrid frame using bolts. The waves on the upper part of the high-rise building were moved by a crane and connected to the frame in the same way as above. The building induced sunlight to enter the entire building through transparent diamond-shaped panels. The building was guided by transparent diamond-shaped panels to allow sunlight to enter the entire building. The sunlight that came through the curtain wall could be effectively spread by the interior lightwell atrium. The lightwell atrium was not in the form of typical glass ceiling, but rather a void space was drilled into the slabs on each floor so that the lower and upper floors could be connected. This allowed natural light to permeate all spaces through the light well, depending on the planar configuration that rotate by 5 degrees in a spiral shape. This had the effect of naturally improving the difference in illuminance between the center and the outside of the building, allowing sunlight to enter the interior office. After the complete construction of the building was completed, there was a question of how the Gherkin Tower applied a different energy efficiency system than other buildings. The Gherkin Tower, designed by Norman Foster, is a representative green building that introduces various innovative systems to increase energy efficiency. What is a green building? A green building is a building that reduces energy load and improves energy efficiency. So what methods did the Gherkin Tower adopt to improve energy efficiency? As the table shows, lighting, cooling, and ventilation account for more than 60% of electricity used in most offices, and heating mainly uses natural gas. To reduce this energy consumption, Norman Foster designed to use natural ventilation to reduce the energy consumption used for heating and cooling in buildings. The heating, ventilation, and air conditioning systems in the Gherkin Tower take full advantage of natural ventilation to reduce the amount of cooling and heating energy used. This is done in the following ways. The console shape of the building reduces wind turbulence and effectively induces air circulation around the building, thereby promoting natural ventilation. The shape, which turned 5 degrees, also allowed for natural lighting. The exterior walls of the building have ventilation shafts for ventilation, which allow natural ventilation and mechanical ventilation to be used as a unit combination. More energy is saved when using only mechanical ventilation. The air in the double glass and outer walls acts as an insulation, maintaining internal temperature and reducing energy loss. Automatic window development system complements the air conditioning through natural ventilation. To regulate the internal temperature, windows are opened when the outside temperature is between 20 degrees to 26 degrees, and the wind speed is less than 10 mph to make the best use of natural ventilation. These sustainable, eco-friendly systems have enabled Gherkin Tower to halve the energy they used compared to similar-sized buildings. Thank you for listening.